Let's do problem number 7 on page 219 of chapter 8. And here's the problem in the book. Zoom in. Focus. God, it takes forever to focus. Okay, so here it is. It says a grinding wheel, 0.35 meters in diameter, rotates at 2,500 RPM. Calculate its angular velocity in radians per second. And B, what are the linear speed and acceleration of a point on the edge of the grinding wheel? So draw a picture of it. We have a grinding wheel. And I just drew it as a disc. Oh, thank you. I always forget. I gotta zoom back out. Okay. So we got this spinning at 2,500 RPM, constant. And, well, they give us the diameter. So in the given, I like to put it as a radius. It's equal to that divided by 2. And we want to know what is the angular velocity in radians per second. What is the linear velocity of a point on the edge out here? And what's the acceleration on it? So let's do the, part A first. Well, what is omega? Well, it's 2,500 revolutions per minute. And I want it in radians per second. So 1 minute is 60 seconds. And 1 revolution is 2 pi radians. So I go like this, 2,500, divide that by 60, multiply that times 2, times pi, and you get 262. So omega equals 262 radians per second after you do the unit conversion. That's just a unit conversion on that. Now for part B, we want to know what is the linear speed. Well, the linear speed is just the radius times omega. Now this r is really the distance from the axis of rotation to where the object is. Now the object happens to be on the outside edge. That's what was given. So you use the whole radius of the disk. But if the, like it was an ant or something, if it was like crawling right here halfway, you would use the radius halfway out there. So be really careful about what r you use. In this case, we're going to use, well, I'll just say the 0.35 meters divided by 2. That's r. And then what is omega? Well, we got that 262 radians per second. And so V is equal to 0.35 divided by 2 times 262, and we get 46, or 45.85, but I'm going to round it off to 46. Now, here's the tricky part. It also wants to know what is the acceleration. Now, some of you were said, oh, okay, well, acceleration equals r alpha, and you tried to use that. But this doesn't give you the whole acceleration. This only gives you the tangential acceleration. This gives you the rate at which you're going faster and faster and faster. But this thing is spinning at a constant rate of 2,500. In other words, alpha is 0. So this is just going to be 0. But you could also have, a radial acceleration or a centripetal acceleration, and there's a couple of equations that you can use. I'm going to use r omega squared. This all comes from v squared over r, and v is equal to r omega, so you can do a substitution and you'll get this. You can also do v times omega, which is the same thing as r omega squared, actually. So that's 0.35 meters divided by 2 times 262 radians per second squared. So the total acceleration is just the radial component of the acceleration. Oh, crap. Hold on. 0.35 divided by 2 times 262 squared. And you get 1.2 times 10 to the 4 meters per second squared. Now this is really just the centripetal acceleration. This is the rate at which you're changing the direction of your velocity vector. But since the tangential component is 0, this is all you got, is this. Now if this was accelerating, you would have to add the tangential and the radial components, but you have to add them as vectors. Remember, they're 90 degrees apart, so you would have to use Pythagorean theorem and all that. But that's a different problem. That's another problem. Any questions on problem number 7? Okay, that is all.